swept wing case. Okay. Basically, we derive the equations for swept wing for the static aeroelastic problem, and here you will see the coupling of bending and torsional deformation. Okay. But just for understanding, if you say this is your swept wing, when the wing is bending, you take bending about what axis, that is the essential part, and twist is about what axis. In our formulation, we will talk about bending of this elastic axis and twist about the elastic axis. So, which is like, if you take, this is my some y bar, because I will later draw a bigger picture, y bar axis, my bending is W as a function of y bar. See, even though the root is a little skewed, you normally take it like this, as though this is my root. This portion is neglected. Essentially, you take it as though this elastic axis is perpendicular to the root, and you have bending of this and a twist about the elastic axis. Okay. So this is what is formulated when you are talking about swept wings. Whereas a straight wing, we took it elastic axis, we didn't bother about the bending problem. Why? Because here, if I take any section which is perpendicular to the elastic axis, this is my bending. Assume that it is only bending pure. So you will have A, B. If it is just bending, you will find A and B will have the same displacement in the plane normal to the board. But if I draw this streamwise, this is streamwise and this is chordwise. Okay. If I look at, because my flow is in the streamwise direction, that is why I take streamwise is as though the far field flow, how it is coming. If you look at this, these 2 points should have the same deformation out of plane. This point will have slightly less because it is closer to the root. So the point C will be slightly having a less deformation than B. That means if you take AC, there is like a twist. Okay. But this is from the streamwise approach. Now the formulation, here you say, hey, how do I actually formulate? There are 2 ways of formulating this problem in a, I would say, approximate manner. Because otherwise if you do influence coefficient, every point take a load, what is the deformation? Like a plate, like a highly tapered wing. Then it is like a plate model you are considering. You are not considering a beam model. Here we are considering it as a, so the beam Now if you look at this, I have one is stream-wise if I stiffen my structure. That means all the ribs in the structure I place like this. Okay? That means I have stiffened my structure in the stream-wise direction. The other case, I can take a slightly, I do chord-wise stiffening. Okay? Then you need to, for the beam bending problem, you treat it, both of them in slightly different fashion. Okay? But as it is, we will say that we have two types of formulation. One chord-wise, another one stream-wise. But there is a slight difference between these two, please understand. When you take chord-wise, your W theta for both cases is only about the elastic axis. Only thing is how you have formulated the problem, the bending problem and the torsion problem, the coupling. That will vary depending on whether you have taken it stream-wise formulation or chord-wise formulation. And these two formulations will be different. The equations will be different. Okay? Then you may ask which one is right. Right? Essentially, this is all approximate method only. Okay? Chord-wise is more approximate. Chord-wise you will find how we couple. That is a very interesting way of coupling. But stream-wise is a little bit better, I would say. Okay? So you can take stream-wise formulation. We will derive both chord-wise as well as stream-wise formulation. And then in the example which I give you as an assignment, you can solve by both approaches to find out how the divergence speed varies depending on your approximation. Okay. First, let us take the stream-wise formulation. So we have to define, draw a diagram, slightly bigger diagram, and then maybe I will draw it here so that I don't have to come back. This is my x-axis, and let us say my aerodynamic. This is my elastic axis, which I call it as y bar, and my rotation is theta bar, and the aerodynamic, this is the aerodynamic center axis, and this is the center of mass axis. And we will define, this is my y axis, this angle I take it as speed. Please understand. This is my origin, that is the elastic axis I am taking. Okay? And the x is along the flow. Now, my length, various length which I have to, this is my length of the wing, and any location I go here as y, and I draw a This is the effective okay, and I go this is L bar. Okay. So you please note down wherever I put a bar quantity, that is defined in the y bar axis. Okay. Same thing we will now describe this is a small section of the wing in the streamwise direction, okay, and this is along the y-axis. And these distances, please understand, this distance I call it D, and this distance call it E, and the chord is C. You may mark some center points here. Take it, this is my card. So C, D, E, they are all measured in the streamwise direction. Okay. Now what we need to get is, we have to get the distributed aerodynamic load, and then the transfer, whatever each section you say this is my aerodynamic center, so I am going to get my aerodynamic load in this, transfer it to elastic axis, and this is of course the gravity load which will mass center, transfer it here. So you will have a force and a moment. The moment is along, please understand, this axis, so I am going to call T is the twisting moment which is along this direction. Okay. So let us write distributed force. Distributed force will be, I use the symbol Z, Y. This is nothing but dynamic pressure chord CL minus N mg into dy. Distributed force on an element dy, basically. This is the lift, this is the gravity, and then distributed moment. But please understand, this is mass per unit length, chord CL, which we don't know. I am only saying CL. Later quite a bit of discussion will go in how do you define CL for a swept wing. Okay, because all the theory what you have learnt is, you put an aerofoil, flow is coming normal to the leading edge. That's what you take. Here the flow is not coming normal to the leading edge. So that part we will describe later. Right now we take it, there is a CL lift coefficient and N is mass per unit length, N is the load factor. Now you take the T y. This is distributed moment. Moment or torque, I would call it distributed torque. Okay. Twisting moment. This is Q C CL into offset between the aerodynamic center and the elastic center plus Q C square CM AC minus N mg d dy. Okay. Now we have got, I would say, the forces and moments. But please understand the geometry of this. I am having a moment along this, and the force is normal to that. Okay. But I will write my equation, bending and twisting, about y bar axis. That means this is my effective route. I take this is perpendicular to the elastic axis. So I have my standard bending theory. But in doing that, we have to be a little careful in the sense, what is my dy? Because the element along this, along the elastic axis, is dy bar. This is dy streamwise. I have to get dy bar. So you will have dy is dy bar cosine lambda. Okay? Because this is dy bar and okay. So this is this is nothing. This is dy bar. Okay? And you take this is dy. Okay? Don't take the other way around. That's what I am saying. The reason is this angle is 90. You follow? That is, along this I am taking this strip. So this is what I have taken. Now what I go is, I substitute this in these places. Even though these quantities Q, C, everything is along streamwise direction, but I am now getting Z, I'll put it y bar, please understand, will be, I'm just modifying it, that's all. Q, C, CL, this will not change, minus N mg dy, I am putting dy bar cosine lambda. Lambda is the sweep. Okay. That means I am getting distributed force along y bar, but if I divide by dy bar, I get force per unit length along dy bar. Force per unit length, that's all. Similarly, I will write torque or the twisting moment. This will be Q C CL E plus Q C square CM AC minus N mg d, again dy bar cosine dy bar. Okay. Now please understand. Again I am insisting that this is dy bar. These are all streamwise. In the chord-wise formulation, the whole thing will become along chord. Okay. Now we have to write the equation for bending and torsion. What we have is, please understand, this T is along what direction? Still, this is along this direction only. Okay, but only thing is, I have defined my T y bar, that is, in the sense, if I divide by dy, the twisting moment per unit length along the y bar axis, but direction is this. Okay, I have to resolve this T, one along this direction, another one will go perpendicular to the elastic axis. What will happen is the perpendicular component is like a bending moment, because if I resolve T, one along y bar axis, another one along this is a twisting moment. This will twist and that will also twist. The twisting will become like a distributed twisting moment in the bending direction. Okay, and that's what we have to now resolve it. So I have my, this is T, I'll put it y bar, that's all. I will get a, this is my lambda, this is my twisting moment, maybe I will call T, twisting moment along this, which I may, if you want to put a bar, I may put a bar also. So that this is the twisting moment along y bar, along the y bar direction. And then this will go like a bending moment, which I may call it as maybe M bar. Okay. Now you know that what is this value? This value is into cosine lambda. This will be sine lambda. Okay, and I have the expression here. So I go put them back here. Okay. Then I get M bar y bar is the moment, bending moment that is acting on the wing along y bar direction over a small elemental length dy bar. Okay, if I divide by M bar y bar by dy bar, that will give me moment per unit length along the elastic axis. Here same thing, if I divide that by dy bar, I will get the twisting moment per unit length along the y bar. Now I can go back and write my equation. So what I will do is, I erase here. I will write the two equations. The bending equation, first we will derive the bending equation. Bending equation is what? We know that bending moment is EI d square W y bar. Please understand, W is the normal, or I would say the bending displacement of the beam along the elastic axis. That's what I am taking, W. I am not putting a bar, I am just taking it as W. If you want to put a bar, you can put a bar. Okay. Divided by d y bar square. This is nothing but my distributed moment per unit length. Okay, distributed moment per unit length. Alright, moment per unit length will be at any section. The moment will be due to the aerodynamic lift which is acting along, that is due to Z plus the integral of the component of the twisting moment for the bending. So you will have two components. So I can write this as Y bar to L bar. Z bar, I am using now a symbol zeta bar, eta bar minus Y bar d eta bar. Okay. Minus, maybe I put it here, minus integral Y bar L bar M bar eta bar d eta bar, but this is I have to take this quantity is per unit length. That means I have to divide here per unit length. Dy bar is existing everywhere. So if you want per unit length, you divide by dy bar all over the place. Okay? That is essential. That is why even though I use the same symbol, here it is per unit length. Alright. Now what you do is, this expression you already got from here. And this z bar, I am just simply changing because this is zy bar, I put a z bar. That's all. Okay? So, z and y and eta, these are, that is eta I am taking now. Please understand, this is my eta bar. This is a running variable. Eta is a running variable. I am getting at any y bar is nothing but eta minus y bar. This force into eta bar minus y bar is the moment. Similarly, I have to add all the, because I put a minus sign, the reason is this moment. This is the twisting moment which is like this. So when I make a component, this will try to bend it down, whereas the Z force will try to bend it up. Okay? That is the reason I put a minus sign here. Okay, now what you can do is you can take this quantity, you differentiate twice. If you differentiate twice means first differential d by dy bar of ei okay, this is becoming you will have to, I can write this integral into two parts. One integral will be minus y bar, that will become simply y bar n bar, z bar eta bar d eta bar. That is, I am differentiating with respect to y bar. This is one term. Okay, y bar integral z bar eta bar d eta bar. Then the second term will be minus y bar integral of differential of the integral quantity. Integral quantity, if I differentiate, I get the same function. Okay, but I have a minus, so this will become minus and then this is another term, integral y bar f bar eta bar z bar eta bar d eta bar. That is the other term. If I differentiate it, I will get simply the same integrand, but since this is a lower limit, I will put a minus. This will become y bar z bar y bar. Then of course this will be plus m bar y bar. Okay, please understand, this is how these two terms correspond to the first integral. This term is just this term. Now you will find these two will cancel out. Okay, they will cancel, leaving behind only this term and that term. Take one more differentiation. When you do one more differentiation, you will have d square over d y bar square ei d square w over d y bar square equals, this is minus y bar, so this will become z bar y bar. This is my distributed force lift plus d over d y bar of m bar. Okay. This is my bending equation, and my torsion equation is basically d over d y bar gj d theta bar by d y bar equals twisting moment minus this term per unit length you will put. That is nothing but minus, I will put it t bar. Okay, this is per unit length. Please understand, here it is over a length of dy bar. So I have to get per unit length. Okay. So please note, this is per unit length. Same thing here also, this is per unit length. So I have my bending equation, I have my torsion equation. Only thing is, what I have to do is I have to go substitute the respective terms. Respective terms is, you know that this is ty bar, I take it from here, put it here, this will be cosine square lambda, and only thing is dy bar will go off because that is per unit length. Okay, so my twisting moment is essentially this term without this with cosine square lambda, and my m bar y bar will be sin lambda cos lambda. Okay, now this is my complete equation. What I will do is I will write that equation here so that it becomes clear. So you will have your bending and torsion equation. This is the bending equation. You will have d square over d y bar square ei dy bar square equals, first term is z bar y bar, that is nothing but this per unit length. You will have q c cl minus n mg cosine lambda. That is this term. And the second term is d by dy bar of m bar thing. that is nothing but sin lambda cos lambda you will have. So you will put Q C CL into E plus Q C square CMAC minus N mg d cosine lambda sin lambda. And my torsion equation is d over d y bar dj d theta bar over this equals, that is minus t y bar. T is this. So you will have minus Q C CL into E plus Q C square CMAC minus N mg d cosine square lambda. Okay. Now this is my complete equation. I have to split now. So what I do is I erase all this part. Okay. Now I will be writing. This is where slowly you have to. What is my CL? CL appears in both. That is my lift coefficient. Lift coefficient, if I split it into two parts, that is, one is due to rigid, whatever initial setting angle of attack. Another one is due to the elastic twist. So I am basically splitting my CL as CL rigid plus CL elastic. I still do not know what is this. Rigid is, you can say CL alpha into alpha rigid. But here I have to know what is the deformation, the change in angle of attack due to deformation. Okay. Now if I write this, you go ahead, substitute here in every place, collect the CLE terms and put it to the left hand side. Alright. And then write the rest of the terms on the right hand side. What we can do is, we will write that part because that is fairly simple. Only thing is I will put it in a very simplified form so that this exercise is just algebra. So you will have d square by d y bar square into EI square. Okay. And here you will get one term with the Q C CL E cosine lambda. So that will come. So you will have a minus Q C CL E cosine lambda. And you will have another term coming from here. That will be minus d over d y bar of Q C CL E into E cosine lambda sin lambda. Okay. Equals the rest of the terms. You can write it as equals Q C CL R minus N mg cosine lambda plus d over d y bar of, you will have Q C CL R into E plus Q c square cm ac minus n mg d cosine lambda sine lambda. Okay, and the torsion equation in the same way you will write it as d over dy bar dj d theta bar over b y bar plus q c cl e into e square lambda equals minus, you can have q c cl rigid into e plus q c square cm ac minus n mg d times cosine square lambda. Okay. Now here what is done is, because this term q c cl r e q c square, and that appears in both the places, so you can write it as one term, some f or something like that, but this will stay as it is. Now you look at it, these are all, the right hand side is independent of the deformation in both the equations. The left side, we need to get still what is CLE, okay, lift coefficient due to deformation. Alright, now that we will go a little different. How we have defined our lift? Yeah, that is where we have to go back. We wrote our equations, bending and torsion. How are we defining our lift? Okay. Streamwise. Now streamwise, what is my angle of attack? Okay, because this is my strip, please understand. I got my lift force on this strip with the card C and also offset E, everything. Now what is my angle of attack? Because of the deformation along y bar axis, I need to get what is the change in angle of attack due to the deformation of the wing along y bar axis. So if I erase here, so the equations are there, so we can keep this set as it is, and we had our, this is my y axis, this is my y bar axis, okay, and I have a theta bar twist and also a bending twist, which I am taking W is coming out of plane. Okay, so I am having a bending twist which is right. This is perpendicular to y bar axis. I want to know what is the change in angle along y axis. That is my elastic, you can say, change in angle of attack due to these two deformations. So that will be along y, I call this as theta. So theta will be theta bar, which is a function of y bar, into this angle is lambda, cosine lambda. This will go because this is lambda This is lambda, so this will go sine lambda, you will get minus okay. Now this is my change in angle of attack. Basically this is my x-axis. I got my change in angle of attack. But how do I get the lift? Okay. Now this is where I will do a little bit of some kind of equivalent lift formulation. Okay. I am using equivalent lift formulation, and that is what will be used, because you need to know what is my CL alpha. Is it like I will just directly multiply CL alpha here, or the CL alpha is different because of the speed. Okay, this is done for a infinite wing formulation. What you do is, I go back and write it here. We know that this is dy and this is dy bar, this is lambda, and similarly this is C and this is C bar. Okay, this is 90 degree. Here this is 90 degree. This is again lambda. Okay, please understand dy is dy bar cosine lambda, and here C bar is C cosine lambda. Now, from our basic theory, two-dimensional aerofoil, the lift on a 2D aerofoil where the flow is normal to the leading edge, okay, that is lift for a span. I will take everything, I will convert into different form. What I am having is, I am having lift will be half rho u is the oncoming field, but normal to the strip is u cos lambda whole square. Okay. Now, what is the area? Okay. Area, you know that if you take okay, this is my strip C is this. Another one is I take I should take it like this, not this way. Let me put it this way. I draw the diagram again. Better. See, I draw like this. And this is dy bar. Okay. This is guard. This is C bar. Okay. This is my dy. Okay. This is nothing but C. The area, whether you take stream-wise, card-wise, it is the same. Okay. Now I will take, either I can write it C bar dy bar because this is along the normal to the u cos alpha, okay, times this is my dynamic pressure area, and you have to have some CL alpha times alpha. Okay. Alpha is any general angle, that's all. It's the angle of attack perpendicular to this flow. Now the question is, I want to know what is my CL alpha when the sweep is not equal to 0. Okay. I have to lift divided by basically what I am taking. Please understand, CL alpha in the direction streamwise. Please understand, this is streamwise CL alpha. This is normal flow CL alpha. This will be, I will divide by half rho. What is my u square? Because the flow is u square velocity. What is my area? Area is C dy. And my angle of attack is, if this is alpha, I will have alpha cosine lambda will be my angle of attack. Okay, so I am going to put here alpha cosine lambda. Okay, because alpha is the angle in this direction. Okay, so alpha cosine lambda will be there. Now if I substitute this lift here, I will get an expression where I'll put it here. CL alpha for lambda not 0, streamwise. This is streamwise. What is that? CL alpha. This is equal to, this is when the flow is normal to the leading edge. So that means I am going to call this CL alpha for sweep 0. Now if I substitute this expression here, you will get one cosine lambda will cancel, rest of the terms will remain as, because C dy is nothing but C bar dy. So that area is same. So you will get this into cosine lambda. Okay. Now please understand, this is valid. If you have a streamwise lift coefficient or the slope of the, because this is basically lift curve slope. Okay. This is normal to the leading edge. Whatever, if you do in an internal experiment, whatever normal to that you have to multiply by cosine lambda to get the lift curve slope with sweep. Now in all these problems, we said it is a wing, everything. That means it is a finite aspect ratio. It's not an infinite wing. So what is my CL alpha? You have to correct for aspect ratio. Please understand. In an approximate manner. Okay. You can take the elliptic loading or non-elliptic also. There are some expressions. You just take that is what you take the corrected CL alpha, and this is with the sweep. That is without the sweep. Now what you have to do is, I know my theta.
So that one 1 by cos
Where?
the equation
1 over cos. No. It is only cos.
So then it will be, this cos lambda will be mu.
No. See, this is the cos lambda. This is here. Cosine square. Okay. Huh? This is with the sweep 0. Please understand, this is the CL alpha for when the flow is coming normal to the leading edge. This one. This is not normal to a leading edge. This one. That is why I put lambda not 0. This is with lambda 0. Okay. Now you got this expression. You go back and write, I know my theta. So in this equation, wherever you have CLE, you will write CLE is CL alpha for lambda equal to 0 cosine lambda times this factor sine lambda minus dw by dy bar sine. So this is my expression. Alright. Now you need to know the boundary conditions also.
So that will be cos lambda theta bar.
Yes, that will be cos lambda.
Oh, sorry. I'm sorry. Yeah, theta cos. Yeah, I'm sorry about that. Yeah. Okay, this is my CLE. Now please note that this term will go and then sit here. Alright? Now you see that CLE contains a derivative of dw by dy and also this term theta. Okay. Now this is my full coupled equations, and in this particular problem, of course we will write the boundary conditions. Maybe I erase this part. Okay. The boundary conditions I will write it. Boundary condition is at the root, because the boundary condition is for a beam which is twisting and bending with the effective root. So you are at the root, you will have your twist theta bar 0 is 0 and W0 is 0 and dW over dy bar at 0 is 0 because slope is 0. Then at the tip you will have
Del theta by dy.
you will have again here Gj d theta bar by dy bar at L 0 because that's a free edge, and then you will have Ei d square W by dy bar square is 0 at L and d by dy bar of Ei d square W, that is the shear force at the other end is 0. Now this forms the complete set of equations. Okay. Now a little brief description. You will have here first derivative expression will be sitting. Okay. First derivative expression, and then you will the operators will become essentially non-self-adjoint. Okay. So we had done the self-adjoint operator almost solution earlier. Now this is going to become a problem with the non-self-adjoint operator problem. Okay. Therefore, the solution technique, what you have to adopt is by Galerkin method. You directly take this equation, assume W a function of y bar which satisfy these boundary conditions. And then similarly you take theta bar, a function of y bar, another approximate solution which satisfies these boundary conditions. Substitute them there, multiplied by the assumed shape function, and then you apply the Galerkin approach and solve for, because you got the equation, I explained to you how to get the divergence problem. You will have a stiffness term, you will have another term with the Q dependent. Then solve that eigenvalue problem. Okay. And you start with zero sweep. If you put zero sweep, you will see immediately the bending will be decoupled from torsion. Okay, that is why when I put lambda 0 everywhere, you will find that here first of all theta becomes theta. So here itself theta becomes independent of W. Okay, and this also you will find that W will be different, theta will be different. That is why for straight wing you solve only torsion divergence. Whereas when you do swept wing, you have to solve both of them and they are coupled. Okay. Now if you want to eliminate coupling, this is a little different. Eliminate coupling in the sense, put E 0. That means what I am saying, my elastic axis is coinciding with my aerodynamic center. The moment I say elastic axis is coinciding with my aerodynamic center, torsion equation is independent. Because torsion is not influenced by bending part, because this term is 0. Because the CLE only is the coupling term. Please understand that CLE which couples. Now the W is also, because that this term itself is 0, therefore it goes off. Okay. Therefore I will have torsion equation. But in the bending, this will have theta. Okay. Bending equation will contain that. Torsion will be independent. Now you can have, that's what we say, bending divergence. Let's call it bending divergence. You can. Your problem, I will give to obtain the divergence speed of the wing. Otherwise you can solve the elastic deformation also. That means the elastic deformation, you put what is the rigid angle of attack, what is the dynamic pressure Q, then you have all these properties, and you can find out if it is a level flight, n is 1, and distribution of mass, you can find how the wing deforms. Okay? I think. Wing, you always write CL alpha becomes CL alpha for infinite wing. This is infinite. Divided by 1 plus CL alpha infinite. by pi into aspect ratio. This is a elliptic lift distribution. This is the
Otherwise we'll put a E there.
Otherwise you will put the 1 plus tau over 1 e, the correction factor, you will put it and then you take this. So this will only change your CL alpha for aspect ratio problems. Okay. If your aspect ratio is very large, you say that this is lifting or whatever it may be. Otherwise, if you take it, this is a 2 pi, that means this will become pi and pi will cancel, 2 over aspect ratio will come. Okay. It will be 2 pi. Or they will say you can take the 5.73 also sometimes. So this is only changing your correction. But this is, wherever this comes, you replace this part. Okay, so aspect ratio effect is also taken into consideration in solving this problem.